In this video we will dig a bit deeper into assembly programming, but before we start with that, some words about this ASI file that you used for generating the virtual machine and also the assembler. ISA is short for Instruction Set Architecture, and this is also sometimes called an interface between software and hardware. What you created with the ISA file was the virtual machine for the ULM based on this description, this ISA file. Now, a virtual machine is actually not hardware, but you also could create from this ISA file some hardware description in form of system Verilog. And with that you could realize this actually in hardware. You also created an assembler where you could use, for example, instructions in some symbolic representation. For example, this add queue, which was, for example, adding register 1 with register 2 and stored the result in register 3. Or add queue, which was adding the immediate value 1 to register 2 and stored the result in register 3. And then the assembler can generate from this assembly notation some machine code, which then can run on this hardware. Whether it's actually hardware or a virtual machine doesn't matter. Actually, let me draw this into this picture like that. From this hardware description, you can generate a virtual machine, or you can generate actual hardware, or you can generate some super hardware, some advanced hardware. For example, hardware which is able to do instructions in parallel. Let's go back to this example actually. If we would have this instruction followed by this instruction where we actually write the result into register 4, then these two instructions do not conflict with each other. We could run this instruction and this instruction at the same time. And stuff like that we could do on some advanced hardware. The advantage of separating this software side and this hardware side with this ISA would now be the following. If you have some program written in assembly for this architecture, it doesn't matter on what actual hardware it's running. If you would use this advanced hardware, it would just run faster without changing the software. Now, you don't have to do assembly programming to take advantage of this abstraction. You actually want to use usually higher languages like C, C++, ABC, Rust, Golang, whatever. Now, all these languages, let me denote them here, and so on, just generate assembly code for a certain architecture, and now you have the advantage. Whether you write C code, which in the end runs on a virtual machine or on some simple hardware, like this ULM on a FPGA, or some superscalar hardware, doesn't matter. You don't even have to recompile your C program. Once from the C program was generated some machine code for this architecture, it will actually run here, 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 or whatever other implementations for this architecture will be provided in the future. And of course the same is true if you write a program in C++ or ABC or whatever. So that means all these languages, these compilers for these languages can immediately take advantage if you provide a better implementation of this architecture in form of hardware. Later in this lecture you will design your own ISA. That means you will come up with your own ISA file, and with the ULM generator you will then generate your own hardware and your own assembler. So let's already look into the ISA file that we use for the next exercise. And there you will see there is a first part containing descriptions for different instruction formats. And the second part contains descriptions how different opcodes use certain instruction formats, how these instructions are mapped to certain parts of the hardware. Think of modules of the hardware, for example, how it's mapped to a 64-bit adder. It also contains descriptions for the assembly notation and also for documenting the instruction itself. Let's consider one example, this instruction format here. Now this part here describes that if you have a 32-bit instruction, let me draw it here, then these 8 bits here are the opcode. The next 4 bits are denoted as Z. The next 4 are denoted as Y. And the remaining 16 bits are denoted as immediate value, or IM. And here you see that opcode hex12 is using exactly this instruction format. And here you basically describe how these fields are connected to this 64-bit adder. You also see that we have here a description for how to actually write this in assembly. You describe here the assembly syntax, that, for example, this % prefix is used for addressing a register. You can change that, for example, if you want. And you also see that we have here a documentation part, which will show up in the reference manual. So in short, if you don't like anything about the assembly notation, you later can change it. If you have a good idea for improving the hardware, change it. But now back on track, and now we actually get started with doing some assembly programming based on this instruction set architecture. This is the flowchart for the Hello World program that we studied in detail in this ULM on paper exercise. It's describing the text segment of this program, the instructions that are executed, and you will see that each box will become exactly one assembly instruction. Let's begin with the first box. This will become load set for 0 extended, load the 0 extended immediate value hex to 0 into register 1. This box, the fetch instruction, becomes move the 0 extended byte into a quad register. We want to fetch something from the address stored in register 1 into register 2. Now about this meaning of byte and quad word. A byte is a byte, 8 bits. Quad word, this is from the Intel world, where they talk about words, which means 2 bytes. And a quad word, therefore, is 4 times 2 bytes or 8 bytes, so 64 bits. So if you don't like that, come up with your own assembly notation for your instruction set architecture. I'm just showing you here basically what I am used to, because I learned assembly programming in the Intel world, and I was using something called the AT&T syntax for that. Also, if you, for example, don't like that, the meaning of this round parenthesis means that you're referring to something at the end of a pointer. So maybe you also would prefer here some notation like asterisk %1, and you can do this in your instruction set architecture. But let's go on here. The next instruction is subtracting 0 from register 2, and you can use the subq instruction for that. You want to subtract the immediate value 0 from register 2 and store the result into register 0. So here you have to read this operands from left to right. You want to subtract this here from this register 2 and store it into here. Some people would prefer something slightly different. Maybe write it down in a reverse order, the operands in a reverse order. You want to store something in register 0, which is register 2 minus 0. Then you have to read it from right to left. And the advantage of that would be, of course, that you can think of it like register 0 becomes register 2 minus 0. This is the so-called Intel syntax, and this is the AT&T syntax. or at least that's how people call this difference. Again, you can use later whatever you prefer. This here is a jump instruction. Diamond shape means it's a jump instruction, and it's a conditional jump because you have here these conditions. This becomes jump if the zero flag is 1. And here we have to jump forward a few instructions. If we jump forward 4 bytes, we end up at this instruction after 8 bytes here, 12 bytes here, 16 bytes here. So we have to jump forward 16 bytes if the condition is true. This here is simple. You already saw that before. We want to print the character stored in register 2. That means in register 2, the low byte contains an ASCII value, and this will be printed out with put C %2. Incrementing register 1 by 1 means you can use this add Q instruction. You have the immediate value 1, you add it to register 1, and you store it in register 1. This here is an unconditional jump instruction. For that you can use this jump, which is jumping back 1, 2, 3, 4, 5 instructions. Each instruction has 4 bytes, so we have to jump back 20 bytes, minus 20. And then we halt the program. And for that we can use the halt instruction with an exit code specified here as an immediate value hex for 1. So that's it, that's the text segment, and here you see it in a nicer form written down. Also recall that you need here some indent, because as you later will see, this first column is used for labels. Now if you type this into a text file, hello.s for example, run the ULM assembler and look at the generated output a.out, you see the following. So this is the machine code for the text segment generated by the assembler, and you see, for example, that this machine code was generated from here. It will be at address 0 when the program gets loaded. This instruction here will be at address 4. It was generated from this instruction, and so on. Now this program will not print hello world because what is missing is the data that should be printed. Now do the following. Also add this here. This is a directive which instructs the assembler to generate a byte sequence for the string 0 terminated. Now if you haven't already done it, now stop the video, write this into a file hello.s. .s is the usual extension for assembly programs. Run the ULM assembler. So ULM as hello.s. This will generate a file called a.out, assembler output. Then again, look into it, and then you see again, this here are the instructions for the text segment. And here you see what this dot string was generating. So this here is, for example, the byte which is terminating the string. And this here is the first character. The first character will be at address hex 20, at address 32. Now, of course, you see that obviously all this is in the text segment, but later you will see you actually can describe the text segment separated from the data segment, then this part will make sense. And then later in the lecture we will also describe the BSS segment, and you will also see the meaning of this hashtag symtab later. But then also run this machine code, for example with ULM a.out to see that it's printing hello world, and then also run it in the debugger. ULM debugger text user interface a.out. Now I want to show you more features to improve things, make it more convenient to write things. For example, what is annoying is that we do have to count how many bytes the instruction pointer should be decremented or incremented for jumping backwards or forward. And for that you can make this change after you tested the previous thing. So if you haven't done it, stop it now. Really do these examples by yourself also. You see what I changed here is that I actually used this column for the labels. I have here a label F, H, and S. And with that you can mark certain addresses, the addresses for these instructions. And then you also can use these labels. For example, here I want to load something from the address that I was marking with this S, the address for the first character in the string for this lowercase h. Then, for example, here I want to jump back to the instruction which was fetching a byte, the instruction which I marked with an F. And here I want to jump forward to the halt instruction, which I marked with an H. Then again, run this through the ULM assembler and look into the executable. And then you will see this. This part actually hasn't changed. The same machine code as before, but you also see here that the assembler was somehow memorizing the meanings of these labels S, F, and H. For example, in the SymTab you see that S refers to an address in the text segment, the address hex 20, which is actually here referring to some data. This F refers to the address 4, the address for this move 0 extended byte into a quad register. This H refers to address hex 1C, the address for this halt instruction. Now the advantage of using these labels instead of hard-coded addresses or hard-coded number of bytes to jump forward or backward is that if you make changes here, for example, if you add a few instructions, then the address of this string changes, the address of this first character. It no longer will be hex 20. Now, when you use labels, the compiler will keep track of the actual address for the string, so you don't have to change the address yourself. Now you can make this code a bit more readable if you also use these equivalent directives, which I use, for example, up here to denote that I'm referring to a register which keeps a pointer. Register 1 is used for keeping a pointer to a character in the string that should be printed out next. And the value at the end of this pointer is stored in this register, register 2. And here I specify that P is a symbol for 1 and CH for 2. Now, if you wonder that this is accepted by the assembler, because I'm using this P up here, but I specified down here, the same thing you actually already did with labels. You were using here the symbol S to refer to something which becomes known to the assembler later. The assembler actually reads this file top down, but more than once. The first time the assembler reads this line here, it cannot generate this instruction, because for generating this instruction, the assembler has to know what is the value of S and what is the value of P. So the first time the assembler sees this line, this instruction here will be incomplete. But the assembler is actually reading this file more than once. Now technically, reading a file is inefficient. Technically, the assembler reads this file into memory, but then it goes over this file, the content of this file, more than once. So the first time the assembler sees this instruction here, the assembler sees that there are unknown symbols, so it will not generate this instruction. But when it, for example, reaches this line, the assembler knows S is a symbol in the text segment with this value. When it reaches this line, it knows that P is an absolute value, the value 1. And when the compiler is now going over this file a second time, it can generate this instruction as you see it. And the same is true for all these other symbols that occur here. And so that means it's okay to define the symbols down here. You also could, of course, specify it up here, but then it's for you. If you think it's more readable for you to first specify these equivalent directives and then use them, do it. In the exercise, we will also deal with cases where the assembler cannot resolve a symbol. You also already can try out the following. Replace this uppercase H with a lowercase h. Run it through the assembler and you will get no error message, which is kind of strange because no matter how many times you read this file, this is an unresolvable symbol. Look into the executable, into a.out, and then you will find in the symtab and also in this so-called fix-up table an entry for this lowercase h with an uppercase u in front of it, which means that you have an unresolved symbol for this lowercase h and then some additional information. For now, it's important to know that you have to be careful when you type in symbols because you don't get an error message if the symbols cannot be resolved. And later I will tell you why this is actually something good, because otherwise you couldn't link together different object files. This is the last example in this video, and here I made more modifications. For example, I have now more meaningful names for these labels. For example, string instead of s, or fetch instead of f, or hold instead of h. And because now these labels are too long to fit into this column and I don't want to use more tabs for the indent, I use a separate line for them. But the meaning of these labels is still the same. For example, this string is a label for the next byte that the assembler generates, the address of this byte. So it still refers to this lowercase h. What you have to do is, if you use labels in an extra line, they need to end with a colon. That's it. But I also made more modifications. For example, I'm using here this .data directive, and I'm also using this .text directive. The .data directive tells the assembler that from now on, all the generated bytes by the assembler belong actually to the data segment. And after this .data, the generated bytes come from this .string directives. So these bytes belong into the data segment, not the text segment. These two directives do not generate any bytes, so they are neither in the text or data segment. Then I change here to the text segment. That means I'm telling the assembler from now on, everything goes into the text segment, and here I generate bytes from here, from all these instructions. And you see that the assembler in the end orders things as they are supposed to be. The text segment should come before the data segment. So you still see that all these instructions for the text segment come in memory first, beginning at address 0, and the text segment ends after this last instruction, at address hex to 0. That means, as before, the data segment begins at this address. And this is what was generated from this .string directive. Also, when you look into the symbol table, you see that string is now a label for the data segment. Within the data segment, it has the address 0. So if you want to know the actual address where this string will be located when you run the program, you actually have to add to this the address where the data segment begins, this address. So plus hex to 0. Here for the fetch symbol, you see nothing changes. It still is located at address hex 4. The advantage of that is that sometimes it's more readable to first describe the data and then what you do with the data. And this makes it a bit more convenient to program in assembly. But again, it's not about learning assembly for the sake of later only program in assembly. It's about understanding what is actually going on the machine, and most of all to understand what a compiler for a higher language is actually doing for you.